Hello, Cal Kids. Today, this is Mr. McKellen, and we're going to talk about checking for convergence of two special functions. This will lead us to what's called the P rule. And what we want to examine today is we have two very similar sequences, 1 over n and 1 over n squared. And we want to see do either of them converge. So we're going to start with both, and we're going to do the ratio test. And the ratio test says the limit as n goes to infinity of the nth plus 1 term over the nth term, and if that is less than 1, we have convergence. And if it's greater than 1, we have divergence. And if it's equal to 1, we have more work to do. So we're going to utilize that test, and we're going to do it on a side-by-side comparison of 1 over n compared to 1 over n squared. So let's start out with on the series on the right. On the left, we're going to write out the n plus first term over the nth term, and that's going to be and then when we multiply by the reciprocal, we end up having to use L'Hopital's rule, which results in a limit of 1. We do the same exact thing on the right side, and we would do a limit as n goes to infinity and then we FOIL, and then we evaluate the limit, and we have to end up using L'Hopital's rule because we get an indeterminate form. We end up getting 1 as well. So what this basically means is we have more work to do, and these cases are not determined as far as if they converge or not. So let's take a look at what else we can do. So we have a function that we can actually make a comparison to, because on one hand we have a function 1 over n, which reminds us of the function 1 over x. So what we'll do is let's consider an integral of the area underneath 1 over x, and if we integrate that from 1 to infinity, we have an improper integral, so we have to do the limit as, let's call it b is driven to infinity of the integral of 1 to b of 1 over x dx. That limit will be evaluated after we finish evaluating the integral, and this will be the natural log of the absolute value of x evaluated from 1 to b. And now we take the limit, and we're going to evaluate the natural log of b minus the natural log of 1, and this ends up being the limit as b goes to infinity of the natural log of b, which is also infinity. So what does this tell us? Well, this tells us that the area under this curve is it doesn't reach a fixed finite amount. It goes off to infinity. It's unbounded. So let's just do a comparison, and what we're basically trying to set up here is a comparison between the area under the natural log curve, the curve 1 over x, and to the area underneath that would be captured if we were to take the area of 1 over 1 plus 1 over 2 plus 1 over 3 plus dot 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 1 over n. If we were to add all those up, we'd be basically adding up. If we know that this area here, which is the area under the 1 over x curve, is less than the area of these discrete rectangles that I'm going to draw, which have a size of 1 by 1 for the first one. That would be this one. Half of that. That would be a half. The next one would be a third. And what I'm hoping you see by this argument, that's kind of really rough around the edges, but this argument is showing that the summation of this sequence exceeds what I already know diverges. And since the area under 1 over x diverges from 1 to infinity, then by comparison I have to conclude that 1 over n, if I sum them up from 1 to infinity, also diverges. So that's my first part of this this discussion, is to show that 1 over n, that sequence, is a divergent sequence. Now we consider what is happening with the series of 1 over n squared. Well, we're going to compare it to the integral of 1 over x squared. So we're going to do that from 1 to infinity, and when we do this integral, we have 1 over x squared dx from 1 to b. We're going to limit b to go to infinity, and by differentiating, we have x to the negative 1, a negative out in front, and we'll evaluate it from b, or from 1 to b. Which is going to equal negative 1 over b minus negative 1, which I now plug in the limit as b goes to infinity. I find out that this actually converges to the value of 1. Now, how does this work with comparing it to the summation of 1 over n squared? Well, I'm going to draw a picture of that area, just like I did before. But this time the area is 1 over x squared. So when I'm at 1 this time, this area right here is at the value 1. These blocks that I would be adding up is like 1 over 1, plus the next term will be 1 over 4, plus the next block will be 1 over 9. So these blocks of area, like the first one is underneath and it's 1, but the next block, because the way the function changes, is only at the value 2, its height is only 1/4, and the height of the next one is only 1/9. And these are actually underneath the summation of that area. So we know that the area under this curve before, we found it to converge, and because some of our blocks that are discrete blocks are clearly less than the converging curve, we can say that the sum of 1 over n squared by comparison to a known limit that converges also converges. So this brings up an interesting scenario. We have two summations. We have 1 over n, and we have 1 over n squared. And this brings us into this thing called the p rule, where if you have a summation and of a sequence of terms where the term is 1 over n to the p power, that p determines if this sequence converges or series converges or not. So in this case, if P is greater than 1, you'll have convergence. But if P is less than or equal to 1, you'll have divergence. And that's the basic lesson that we want to get out of looking at this rule. If we go back and we look at the very beginning of our objective, we wanted to use a ratio test, which we did. We found out that the ratio test really just put us in a position where we really can't say anything conclusive. So as a result, we had to resort to another type of test, a comparison test, and we used a clever approach where we do a comparison to a known integral, an improper integral, but all the same, when we work through that integral, we find out by comparing actual physical areas to the actual area under the curve, we can see by comparison that 1 over n diverges where 1 over n squared converges. I hope this is of help to you, and I look forward to doing some more problems later.